Tell me where you want to start or go to next.
Let's start at 15.
At 15?
Yeah, I have the rest of it down.
Okay, you don't have any problems with midpoints?
No, I'm really good at midpoints. It's really simple.
Distance?
Distance formula is also pretty
Okay.
You got your formulas now?
Yeah.
Okay.
Good.
Yeah, David, you just go through the questions and ask them, midpoints or whatever distance.
Yeah,
if they make...
some of these are pretty straightforward, and if he's got them down, I believe him.
Me too.
It looks like he's writing it out correctly here.
Okay.
Yeah, that one's right. Okay, so you said go to the next page, 15? Is this?
It's on the same page.
The second
It's just
page?
over
Is that
it's just to the right
Way on the right in the bottom right-hand corner
of page 1.
of page 1.
Oh, page 1. Oh.
Yeah, 15. You got 15, 16, and 17 down there. Over in the right-hand corner.
I see.
There it is.
Yeah, I had the thing blown up so much that I didn't see the right side of the page.
Yeah, we had problems photographing. So, all right, we're set.
Okay, so 15 is about polygons and the sum of the interior angles. What's the formula for the sum of the angles of any polygon?
For the sum of the interior angles or sum of exterior angles?
Interior. The exteriors always add to 360.
So it would be 180 over n, and n would be the sides of the polygon?
Not quite. The formula you want to remember is n minus 2 times 180. That's the sum of the interior angles.
Okay.
Check it on a triangle. Does it work?
Let's see.
What's the sum of the angles of a triangle?
180.
Okay. N would be 3, right?
Yep.
What's the sum of the angles of a square or a rectangle?
Wouldn't that be 360?
Correct. So this formula works for that. If it works for a triangle and it works for a square, you probably have the right formula.
So would it be 180 no matter what the polygon, or?
No matter what. If I have a 10-sided figure, it's going to be 8 times 180. So they're asking, how many sides does this polygon have? And they're telling us the sum is 2160. Right?
You're right.
This is the sum, and they're telling us that this is the sum. So they're equal to one another. So all we have to do is solve that for n, and we'll have our answer. So let's solve that equation for n. What's the next line?
What they told us to do was cross-multiply, but I'm not quite sure what we'd cross-multiply if we got that.
Cross multiplication is when you have a fraction. In other words, if I had x over y equals a over b, I could cross multiply to get x times b equals y times a. But in order to cross multiply, you need fractions. We don't have any fractions.
So would we divide?
I got two choices. I can distribute the 180 to the n minus 2, or I can divide both sides by 180 and get rid of it real easily. So, do you have a calculator?
Yep.
Do that math, and what we're left with on the left side is that. What do we got on the right?
12.
So how many sides is there in this figure?
Would it be 14?
Correct. That's how you do it. In other words, if they give you the sum, then you merely need to write an equation out and solve it. Now, let's solve it the other way. The other way is where I distribute the 180. Okay? So that would be 180n minus 360 equals 2160. Now I got to add 360 to both sides. Notice how much harder this is. Now I got to divide by 180 again. I'm going to get the same answer, but it's a little more difficult.
It's a mess. So the first formula works all the time, David.
Well, yeah. In other words, dividing by the coefficient works all the time. It wouldn't work if I had something else being added. If I add 1 to that, well, now I can't divide by the coefficient. In other words, I'm not sitting there looking at just that. I would have to first subtract 1 and then divide by 180.
Right. So what you do is factor the 1 out and then divide, then
Right.
follow the formula.
But as long as you have, this is just a coefficient, I could put it in front just as well. As long as I'm solving this, it's easier to just divide by 180 rather than have to multiply that 180 by both of these things. So you always want to solve equations in the easiest way possible. By that I mean the shortest number of steps. Now usually I tell people that my 2 priorities in solving an equation is get rid of denominators and get rid of parentheses. Well, that's not my first step here. My first step here is to divide by the coefficient and then get rid of my parentheses. So it kind of depends on the equation, but
Okay.
all right. 18 next.
Yeah.
Trying to read 18. What is x? X is this angle right here?
Yes.
What's this say?
81.
And that's x.
Yes.
Okay. First of all, 16 is not right. The sum of the exterior angles of any shape at all is always 360, no matter how many sides it has. Now let's talk about what exterior angles are. That's an exterior angle. That's an exterior angle. And that's an exterior angle. If I add those 3 up, it'll be 360. And if I do the same thing with a rectangle, it'll be 360. And if I do the same thing with a hexagon, and they don't have to be regular. In other words, if I get the exterior angles by being consistent with my line extensions, then my exterior angles are 1, 2, 3, 4, 5, 6. If I add up 1 through 6, they will be equal to 360. Okay? So,
Are they all, David, are they all equal angles?
no, not necessarily. They certainly aren't in the problem we're looking at. In other words, it does not have to be a regular polygon. If I had a shape like this,
Yeah.
and I do the exterior angles, they're still going to add up to 360, all 4 of them.
So you don't need a formula to determine the
Right.
number.
This is the easiest one of all. There's you do need a formula for the sum of the interior angles.
Right.
But
And if they ask,
you don't need a formula for the sum of the exterior. No matter what the shape, it's always 360.
right, and the only thing they could ask you about the exterior is how many exterior angles do you have?
The toughest thing about exterior angles is you can actually make 2 sets of exterior angles, and you have to make sure you don't crisscross. In other words, I'm going to start from this vertex right there, okay? So I'm going to make that exterior angle there. That's an exterior angle. Well, when I get up here, I got to make sure I go in the same direction. That's the exterior angle, not Well, it turns out they're the same, aren't they? So
Yeah.
it doesn't matter which way I go. I hadn't realized that until just now. Yeah, but just continue on counterclockwise, extending every line like that, and these are your exterior angles. And you'll notice that the more sides you have, the smaller these exterior angles get. If I had a 30-sided polygon, the exterior angles are going to be really tiny. So that's why they always add up to the same number, 360, is as you get more sides, the exterior angles get smaller. Okay, now on this problem here, we've got we got 2 exterior angles, 2 more. So this is the only one I don't know. What's the exterior angle here?
You add them up and then.
To this 105, what's the exterior angle? That's a linear pair. So they got to be supplementary.
Would it be 75?
Yeah. So this one's 75. And I know that all of them add to 360. So give me an equation that we can solve that's going to have x in it. Start with 76. 76 plus what?
76 plus 75 plus 81 plus 2x equals 360.
You got it.
1800.
And that's easy to solve. Right? In other words, I don't want to waste our time or your time solving this if that's no problem for you. So make sure you verify that when I say that's easy to solve. Okay? Do you need to go through and solve this, or can you solve that?
I can solve that.
Okay. I think so. I thought so, at least. Okay. So let's look at, how'd you solve 17? Give me the equation you used to solve 17. I'm not so much concerned about whether that answer is right, just so long as your method is right.
Well, I knew that all of them added would equal to 180, so I added them all together and set them equal to 180.
180? It's a 4-sided figure. 17.
Yeah, 180.
What's the sum of the angles? What's the formula for the sum of the angles?
Oh, I
Keep going. So how many sides do we have?
We have 4.
So what's the sum of the angles? $360, right?
Oh, yeah.
4 minus 2 times 180. So the sum of the angles has to be 360. And so you just add up each of these. That's what you did, right? You said 2x plus 6x plus 1 equals 180, all of them?
I just set them equal to the wrong number.
Okay, so there's an easy way to fix it. What do I have to do to your answer to fix it?
Would you just double it?
Yep. 39. Is that 19.75?
It's 14.7.
14.75. I was wrong anyway. When you double that, you get what? 29 and a half.
Yeah.
Okay. Number 19.
I have one question, though, about 16.
Okay.
Did you say 45 was incorrect?
Well, if we double 14.75, what do you get? You get 29 and a half, right?
Yeah.
In other words, if I set all of these equal to 180 instead of 360, then my x is going to be half what it should be. So if I double it, this should be right.
I was talking about number 16, not number 7.
I apologize. Yeah, the sum is always equal to 360.
No matter how many sides.
Yeah, I must have set it to
So
180.
it doesn't matter if it's an octagon or a heptagon or a dodecagon.
Bazillion. No matter what, how many sides.
All right, we ready to go to 19?
Yes.
Okay.
No, all right, wait a minute, David, because we're still on, just hold on for 17 for a second.
Okay.
Because you had 29.5, right?
Yeah, and I changed my thing.
All right, so why do you have 45 here then?
Oh, I was checking number 16.
Oh, 16, sorry. All righty. Sorry, David. Go ahead.
Okay, I made exactly the mistake you just made. I thought he was talking about 17 when he said 45. So, okay. So we good for 19 now?
Yeah.
What's this middle line called?
Would it be the midpoint?
It's the mid-segment.
It's,
It does happen, and the reason it's called the mid-segment is because it bisects that side, and it also bisects this side over here that's slightly off out of the camera.
yeah.
In other words, that side is equal to that side of that trapezoid.
Yeah.
So whenever you have a line that goes through the middle of a trapezoid, and do we even know this is a trapezoid? Yeah, it has to be. In other words, if this wasn't a no, it doesn't have to be. Huh. That's interesting. In other words, they don't tell us anything about this figure. Well, I can draw that any way I want, I believe. I can draw it like this. And I can still draw a line that bisects that and bisects this. And that midpoint is not parallel to any of those two sides. However, it would still be the average between this. In other words, if that's base 1 and this is base 3, or base 2 rather, the midpoint is the average, regardless of whether it's a trapezoid or not. They did not tell us that that's a trapezoid, and we don't know that it's a trapezoid. However, this midpoint is the average between the top and the bottom. So, what's the equation? If the middle line is the average between the top two, or the top and the bottom, what can I write? First of all, let's figure out what the average is between the top and the bottom. How do I get that?
Yeah, on the other end, divide by 2.
You got it. 3r plus 11r plus 4. That's the average. That's going to equal that middle one. 6r plus 5. Now, again, I have one equation, only one unknown. So, it's solvable. Let's combine this, first of all. We got a 3r and an 11r, so we can make that 14r plus 4 over 3 equals 6r plus 5. What's the best first step here to solve this?
Well, could you times it by 3?
Yeah, remember what I said about getting rid of denominators and parentheses? Well, I don't have any parentheses here, but I certainly got a denominator. If I multiply both sides by 3, what do I have? This is what I have on the left side. What do I have on the right side?
Would you have 18r plus 15?
Uh-huh. Now what?
Well, then you could just subtract 14r.
Okay, so that leaves 4r over there. What about the numbers?
Then you could subtract 4 from 15.
Okay, and that leaves plus 11. In other words, you missed a crucial part of solving the equation. When you solve equations like that, you want to gather all your variables on one side, all your numbers on the other.
All right, so would you subtract 15 from 4R?
Exactly.
From 4?
Exactly. Which gives you minus 11. Now we can solve for R by just dividing both sides by 4. So that's R, and that's what they want you to solve for. Does that say R? Yeah. Okay?
Okay.
All right. Next page, or?
David,
Yeah.
before you leave, can I ask you a question on 19? You know, when we started the equation, we wrote down the middle average. What you do is you add the two sides together and divide by 2.
Correct.
And it gives you middle average. But when we went to the formula, didn't you divide by 3?
You're absolutely right.
So it should be.
I apologize. That was a horrible mistake. It's late in the day. I'm sorry.
You just got caught by the dumbest son of a bitch in math, David. So I'd be embarrassed now, because I'm hopeless.
Okay, so I wanted to multiply both sides by 2, which makes that 12R plus 10. And then this becomes 2R on the left, subtract 4 from both sides. Well, that's a much better answer. I thought that answer was a little flaky looking, negative something. So, yeah, thanks for that correction. Yeah, whenever you're finding average, you always total and divide by the number of things you have. Well, I guess I made the mistake because I was looking at 3 things. But I was trying to find the average between the top thing and the bottom thing.
Right.
So that's why I want to add that to that and divide by 2. And that has to equal that.
There's 2 lines.
Yeah, yeah. Okay. Do you want me to quickly look at some of the... I don't know. What would you like to do, Patrick, at this point?
We should go to the next page.
The next page?
Yeah.
Okay. This is it? No, this is the same page. Is this,
one with that. Sorry, there it is.
This the next page? Okay. Not sure I can read this well enough to do it. Yeah, I think I can actually.
We can read it too.
Which one? We're going to do the first circled one?
Yes.
22?
Yes.
What's that word say? Kite? So that's kite. That's some kind of trapezoid?
Would you like us to resend it?
Yeah, probably that's the best thing to do. But we can start while you're doing that, or your dad's doing that. So what we need to do is take these properties that are on the left and match them up with kite, trapezoid, parallelogram, rhombus, and rectangle. What's the word above trapezoid? Isosceles?
Isosceles, yeah.
Okay, good. You don't need to resend it. I can figure it out. So, which figures have both sets of opposite sides or parallel?
Would that be a parallelogram?
Correct. Opposite sides are congruent.
Would that also be a parallelogram?
Well, a lot of these are going to I'll write yes or no for each box. Okay, well, let's start again. I apologize. Both sides of opposite sides are parallel. Not a trapezoid. Definitely a parallelogram. Not, yep. Is that a rhombus also?
Yes.
So a yes goes in that box and a yes goes in that box. How about a rectangle?
No.
No, it's yes. Both
Yes.
sides of opposite sides of a rectangle are parallel.
Yeah.
Okay. Let's go to this one. Opposite sides are congruent. Is that true for a kite?
No.
Yeah, they want a yes or no in each box. So we got a no there. How about here? I'll tell you what, I'll point and you tell me yes or no.
Would that be yes?
Well, let's draw a trapezoid. An isosceles trapezoid means these two sides are congruent, but these aren't. Top and bottom are parallel, but they're not congruent. So we get a no for trapezoid. You see why?
Yes.
In other words, that's congruent to that, but that is not congruent to that. So opposite sides are not congruent if I have two of them that aren't. How about a parallelogram? Or opposite?
That'd be yes.
Okay. Rhombus?
Would that be yes?
Uh-huh. Rhombus, remember, is four equal sides. That's what you should always think. First thing when you think rhombus. Four equal sides. Well, that means opposite sides are congruent. Rectangle?
Yes.
Okay. This one says diagonals bisect each other. Is that true for a kite?
Yes.
When I draw a kite, I'm not going to draw it like that because I can't really tell much. It looks too much like a rhombus. So I'm going to exaggerate it so I can tell its properties. See what I mean? I'm going to make the tail longer. Now I can tell a lot by the diagonals. Do they bisect one another?
No.
One bisects the other one, but not vice versa. In other words, the long diagonal bisects the short diagonal, but the short one does not bisect the long one. So we get a no with the kite on that. The isosceles trapezoid. Let me try to draw it so it will be more clear as to whether they bisect one another. No, it's got to be like that. In other words, those two sides are equal. The question is do the diagonals bisect one another? What do you think?
Yes.
Yeah, I think they do too. And they do because that triangle is congruent to that triangle. Because of these parallel lines. In other words, that's parallel to that, which makes that angle equal to that angle. That angle is equal to its vertical angle. And this angle is equal to this angle up here, or rather this angle right here. So, makes them similar. Doesn't make them congruent. This side is congruent to that side, and that makes these two triangles congruent. This one and this one. And if those two are congruent, then that side has to equal that side, and that side has to equal that side, meaning they do bisect one another. So we get a yes there. Parallelogram. Best way to really answer these is to draw one and see if it looks like they bisect one another. Yes? No?
Yes.
Yeah. And they do here for the same reason they did with the trapezoid, which is that we have two congruent triangles. This triangle 1 has to be congruent to that triangle 2 because of all the parallel lines and the vertical angles and the fact that that side is congruent to that side. We're going to end up with angle side angle to prove congruency. But once we've proved congruency, now we know that that's equal to that and that's equal to that. So the diagonals do bisect one another. Rhombus.
Oh, yes.
And rectangle.
Yes.
Okay. The third one, diagonals are what? Congruent?
Yes.
For a kite?
Would that be...
Let's go back to our picture of the kite. Are the diagonals congruent?
Yes.
No, they're not.
I see.
That one's much longer than that one. And that's why I suggest always drawing it a little exaggerated. In other words, if I'd have drawn my kite like this, it's not so easy to see the diagonals are different. But if you draw it with a little longer tail, it becomes obvious that the diagonals are not the same. Not only that, but the angles are not the same either. In other words, this angle is not the same as this angle, but this angle is the same as that angle. In other words, a kite does have one pair of opposite equal angles or congruent angles. This angle and this angle is congruent. Okay. Parallelogram. Well, did we say isosceles trapezoid? No, that was next. Yes or no? There's our isosceles trapezoid.
Would that be yes?
Uh-huh. Parallelogram?
Yes.
Again, draw it very exaggerated. Those diagonals equal?
No.
No. And I can only tell it by drawing it very, very slanted. Rhombus.
Yes.
Yeah, because a rhombus has to be... hold on a moment. Remember, a rhombus merely has to have 4 equal sides. Those diagonals equal?
Well, no.
No, they're not. So the diagonals are not congruent in a rhombus. No for parallelogram. Yes for that. How about a rectangle?
Yes.
Correct. In other words, you can't, no matter how long I draw the rectangle, those diagonals are going to be the same and bisect each other. Okay, so the diagonals are perpendicular. Kite?
Would that be yes?
Correct. Isosceles trapezoid.
Yes.
Again, let's draw it really like this. There's our isosceles trapezoid.
Oh, yeah, I see. So that would be a no.
That would be a no.
So the key really, David, on all the shapes is to draw them out and
exaggerate them. Yes, exaggerate them and you'll be able to see. In other words, you can see with this rectangle that they're not perpendicular either, right? But if I'd have drawn it more like a square, now they look perpendicular. So you can't really tell if you just draw a normal rectangle. But if you exaggerate it and make it look like a letter, you know, an envelope rather, you can see that they're not perpendicular to one another. So the parallelogram, those are not perpendicular. The rhombus. I can only draw the rhombus. In other words, the rhombus has to have 4 equal sides. Those are right angles. So we got a yes for the rhombus. And again, the rectangle, if I draw it elongated, I can see that they're not anywhere close to being perpendicular. And finally, the bottom one says opposite angles are congruent. Okay?
So would it be yes?
No, it's only got one pair of opposite angles that are congruent. In other words, that's congruent to that, but that is not congruent to that. Actually, I should have looked at the long one. In other words, if you look at this long one, you can see that this full angle is not the same as that full angle. So it's a definite no there. Isosceles trapezoid. Is this angle 1 equal to angle 2?
No.
No. So we got a no there. Parallelogram.
Would it also be no?
We're on the bottom one. Are the opposite angles, are they congruent for a parallelogram?
No.
Actually, they are. That's acute. That's acute. That's obtuse. That's obtuse. The opposite angles are equal, always, on a parallelogram. Opposite sides and opposite angles.
Okay.
A rhombus.
Would that be yes?
Yeah, because a rhombus is also a parallelogram, right? In other words, the only difference between there's my rhombus right there. I can erase this part here. And there's my rhombus. Well, a rhombus is also a parallelogram, so yeah, the opposite sides still have to be equal. Or the opposite angles, rather. Rectangle?
Yes.
Okay, we got through that one. 23 next.
Yeah.
Measures, what is those measurements? 50 by 84 or 30 by 84?
50 by 84.
50 by 84. Okay. Find the length of the rope needed to reach diagonally across the court. It's the measurement of x. How do you figure x?
Would you do 84 plus 50 divided by 2?
No? It's a right triangle. We need to use the Pythagorean Theorem. It's another thing you want to be really good at geometry, is solving right triangles.
Would be 84 squared plus 50 squared equals x?
It's the square root of 84 squared. In other words, the Pythagorean Theorem says the hypotenuse squared is equal to the sum of the sides squared. So if I'm writing it, that's what it looks like. But if I'm solving for x, I have to take the square root of both sides. So x is going to be the square root of 84 squared plus 50 squared. And that's always what the hypotenuse is. I'm pondering because as long as you start with the Pythagorean Theorem, you can always solve right triangles. In other words, as long as you start with c squared equals a squared plus b squared, where c is the hypotenuse. Okay? But you have to solve so many right triangles over the last 2 years and the next 2 years, not just in geometry, but if there's one skill in math that it's good to have, is being able to solve right triangles quickly. So I'm normally a proponent of memorize the one formula, and that's the only formula you need. You can always figure everything else out from that one formula. But I actually don't believe that that's the best way to do it on solving right triangles. I actually think that it's better to memorize, if you're solving for the hypotenuse, it's always the sum of the other two sides squared. I mean, it's always the square root of the sum of the other two sides squared. If you're solving for one of the sides, say b, then it's got to be the square root of c squared minus a squared. And if I'm solving for a, it's the square root of c squared minus b squared. So I tend to want my students to memorize those three. And the only reason is that it lets you very quickly solve right triangles, as opposed to having to manipulate this to solve for C or B or A. And you don't really need to remember both B and A, you just need to remember one of them. In other words, to solve for the short side of a right triangle, you take the square root of the hypotenuse squared minus the other short side squared. So if you've got this one memorized, this one kind of follows. So you don't actually need to, find a spot in your brain to memorize this. But do memorize these two. In other words, know if you're solving for the hypotenuse, it's this one. And if you're solving for a short side, it's this one. So we're solving for, and notice that all three begin with the words square root of. And that's the other thing I teach people, is when you're solving a right triangle, the answer is always square root of something. Now, it might be the square root of a perfect square number, so it might end up being a whole number, but it's still the square root of something. Because the biggest mistake people tend to make is they leave off the square root of. So you probably are going to need your calculator for this one. Square 84, add it to the 50 squared, take the sum and take the square root of it. And that gives me that hypotenuse.
He's almost done.
Okay. Okay.
Yeah, squares. Yeah, it's a hard to calculate.
It would be 4.02942.
Now, first of all, the hypotenuse has to be the biggest side of a triangle. Always. So it's got to be a number bigger than 84. Remember, we're doing this one here.
Now follow you. Do this. Do 84 times 84. Square 84.
I was taking the square root of 84.
No, not yet.
No, it's not. That was a mistake.
Yeah, so you know your mistake. You won't make it again. But now just slow down and just do it correctly. Because once you make the mistake, you won't do it again. That's why this is perfect. Have the formula set out like this. Take the time and then do the square root. You couldn't have it the length 4 if it was 50 on one side and 4 on the other. That'd be a weird looking thing. It'd be impossible. It wouldn't be a great triangle.
It's 97.75.
Okay, that makes more sense. In other words, that's a believable answer. I'm not even going to question it. Let me give you a few right triangles to solve with smaller numbers, just because I want you to get used to this. This is a skill that you just can't practice this enough. What's X? Remember, it starts out square root of. What is it the square root of?
The square root of 45?
Well, give it to me piecemeal. I don't know what the final answer is. So it's the square root of 6 squared. What's the rest of it?
Would be plus the square root of 3 squared.
Minus 3 squared. And it is not the square root of 6 squared minus the square root of 3 squared. Both of these are inside the radical sign.
Hey, David, hold on for a second, would you? I think what the problem is he's using the wrong formula. He used C, which is the one.
Right. I was going to point that out next. This is the formula you want to use. In other words, when you're solving for one of the short sides, then what goes inside the radical starts out with the hypotenuse squared, subtracting the other short side squared. See?
Yeah.
Okay. So this becomes square root of 36 minus 9, square root of 27 is what that is. Square root of 27. Okay. I'm going to give you some more, just because practice helps a lot on this. What's X? X is the square root of what?
9 plus 4.
Okay, that's it. 13.
Could you, if you wanted, go all the way and figure out the decimal?
No, you always leave it as a radical. The radical is the most accurate. There's no number more accurate than that. If I turn that into a decimal, I've made it less accurate. Because it's an irrational number, I've got to round it off somewhere. So the moment I turn it into a decimal, it's not accurate anymore. Square root of 13 is perfectly accurate. So always leave these as radicals. Okay, let's do another one. Now remember, here you're solving for the short side, one of the short sides. So what's X equal to?
Would be 9 squared minus...
Hold on. Always start your answer with what words?
Square root of.
That's a big thing, because that's what people forget all the time, is that square root. And what is inside?
9 squared minus 2 squared.
You got it. Those are the only, so you can see that really those are the only two you need to memorize. Because this one, the third one, is just the other short side. In other words, these two are really the same. It just, in other words, if I switch this up and make this 2 and this x, you do the same thing. You still take the square root of 9 squared minus 2 squared. So I don't really need to memorize this one, but I really do believe that it's very beneficial to somebody to memorize both of these, as opposed to starting from this. Most everybody has this memorized. And you could algebraically come up with this. You know, just take the square root of both sides and you can algebraically come up with that. But that's a lot of math to do. And you know, when you're in the middle of a test and you have to solve a right triangle, you don't really want to start from this. It's much better to start from one of these spots.
Hey, David, on that last one, we had 9 squared minus 2 squared, square root of, sorry. So that, would you leave that as the answer, square root of 77? Or would you do the square of it?
Yes. And the reason I would leave it is because I can't simplify it.
Right.
In other words, I can change that into the square root of 11 times the square root of 7, but those are both prime numbers. I can't do anything more with it. And this is not considered simplified. That's 2 terms versus 1. So you leave it as square root of 77 unless you can pull a whole number out.
Gotcha.
In other words, I would never leave that like that, because square root of 20 becomes square root of 4 times square root of 5, which becomes 2 root 5. In other words, I can simplify that. I can't simplify root 10. Root 10 is not simplifiable. It's indeed root 2 times root 5, but that's all further I can go. I can't bring out a whole number. So unless you can pull out a whole number from a radical, it's simplified. In other words, that's simplified. I cannot pull out anything from the square root of 101. That's the way I would leave the answer. But these two things right here, if you're good and fast at solving right triangles, it will make geometry so much easier for you. And I'm really not kidding. You're going to have to do it at least 100 times, maybe this year. But when you take the ACT test, there's at least 10 problems on there where you have to solve right triangles. So being able to do it quickly is really a key thing. Okay. 26 next?
For 26, since we went over 22, which kind of dealt with 26, I think I'm pretty good on 26.
Okay.
So where we would go is 29.
Yeah, don't worry about the time. That other student's in Florida, so there's no way they're still going to be. That's 2 hours later. So I'm not going to have any session with them. So we'll go until you're done here.
29. 29.
I'm not worried about time. I'm just.
He's giving you the ones that we need, David.
Yeah, just what I feel like.
I know. I'm just trying to say you don't need to rush it or anything.
Appreciate it.
Sure. Inductive reasoning is making a logical argument based on proven facts. Deductive reasoning is making a prediction based on prior examples or patterns. Think you may have those reversed. Not positive, but I'm pretty positive that deductive reasoning is when you base an argument based on facts. You deduce something. Well, then again, No, I'm pretty sure you got them backwards. Do you know?
It's 21 hours.
Yeah, I'm pretty sure you're right.
I would have to look up the definition of that. That's not something that comes up a lot for me, even with my 10 geometry students this year. But I'm pretty sure deductive reasoning is based on fact, and inductive is you're going to,
Yeah, you're right. Inductive is based on general laws.
I think so, but is it worth me looking it up? Here, I can find out.
We did, David.
I really.
Oh,
Patrick's got it.
okay, good.
Look,
All right. I just didn't want to give you wrong information. So, all right. 29. Construct a perpendicular bisect through the point L that lies on segment JK. Okay. All of these construction problems start with a line. Just know that. Or two lines. But if I'm trying to bisect this segment, JK, we'll make this point J and this point K. You take your compass needle, make sure that the measurement is more than half of the line. Okay?
Hold on, let me just write this out. Here we go.
It's important to understand that a compass is a way to measure lengths. It's not a way to draw arcs, which is a lot of people misunderstand it. In other words, it's true, you can draw an arc. If I put a needle and draw an arc, it looks like it's a way to draw arcs. But the reality is that what I'm looking at here is this distance is the same everywhere. So what it really is a way to measure this distance. That's what a compass does. Okay? So make the separation between your pencil and your needle be greater than half the length of this line. If I make it less than half, I'm going to draw an arc and it's going to look like that.
And then would you just flip it around and then do it again, and then what's between those?
Yeah, put the needle there, draw an arc. Don't change the measurement. Put the needle there and draw the other arc. Draw a vertical line between that point, and that bisects the line. And you don't need to actually make a full arc. You can do it like this, where you can make an arc up there and an arc down here, and then put the needle over here and make an arc there and an arc there, and now connect the two, all of the intersecting points, and you bisect that line. Let's talk about bisecting an angle, because I'm sure you have to do that also. If I want a bisector, in other words, if I want to draw a line that bisects this angle, put the needle there. It doesn't matter the length of your compass setting. Make an arc there, same distance, so these two are the same distance. Now go put your needle on that point and make an arc there. Put the needle on that point, make an arc there, and where those cross, connect that to the vertex, and you've bisected that angle. In other words, these distances are the same. And what I've basically done is created a parallelogram. Doesn't look like it, but it is going to be a parallelogram, and that's why that diagonal bisects that angle. It's because it's a parallelogram. Remember, the compass is a measuring device. A measurement of length only. That's all it does. Okay, what next, Patrick?
We would do 30.
Okay. They're going to make you do proofs from start, huh? You want to do a 2-column proof or a paragraph proof?
2-column.
Or flow chart? I don't even know. I could figure out how to do flow charts, but we'll do a 2-column proof. So we have our statement, and we have our reason. And let me do it this way. What's the first statement?
Well, that AB equals CD is given.
All of the givens. I'm going to say I'll say congruent, okay. Given. And also AB is parallel to CD. It's congruent to CD and it's also parallel to CD. And both of those are given. So I'm trying to prove that triangle ABE is congruent to triangle CDE. Okay? Now, there's only like 5 ways to prove congruency, right? There's side, side, side. What other ways are there?
You could do angle, angle, angle.
No, that proves similarity, but not congruency.
You could do angle, side, side. Wait, no, that one's also.
Let's talk about, there's 2 of them that have 2 S's. That's one of them, it has 3 S's. The other one is side, angle, side. And then there's 2 of them that have angles. There's angle, side, angle, and there's angle, angle, side. So that's kind of a good way to think about it, is whichever one we use to prove these are congruent, it's got to be based on one of these 4. There's another one involving right triangles, which is HL, but let's not worry about that. That means a hypotenuse and 1 leg. These are the 4 that we are looking for. Can you still hear me, Patrick? I saw there was an audio difficulty.
We're fine.
You're fine? Okay, good. Okay, so my attempt is I've got to show by one of these 4 things that this triangle is congruent to that triangle. Well, what do I know for the moment? If I draw it, I know that that's the same as that. And the only other thing I know at the moment is that those are parallel. So what other things can I say are equal between these 2 triangles?
Could you say angle AEB is congruent to angle DEC?
Yeah. So those, why is that?
Wouldn't it be vertical angles?
Vertical angle theory, or theorem. Okay. What else can I say about angles? Remember, I have 2 parallel lines and I happen to have 2 transversals. So what does it say about these angles? In other words, angle 1 and angle 2.
That they are congruent?
Yeah, because the top and bottom lines are parallel.
That'd be B and D?
Yes. B and D are equal, congruent. Is that enough to prove congruency? I have two angles and a side.
Yes.
Is it angle, side, angle, or is it angle, angle, side? It's one of those two because I have two angles and a side.
Would it be angle, side, angle?
No, always go in the shortest path. Start at one of your pieces of information. In other words, I have three things that I know. I know that, I know that, and I know that, right? Start at one end and go in the shortest possible path to the other end. Well, that would be side, angle, angle, right? Which is the same as that. In other words, I can go in either direction. I can also say angle, angle, side, but what I don't want to do is go in the long direction. I don't want to go this direction. If I go that direction, I get angle, side, angle. And that's not the theorem that proves congruency here. It's not angle, side, angle. It's, I'm going to go in the shortest distance between these three pieces of information. And that's to go either this way, that, or go this way, this. And it's hard to see here why that's the shortest path. Do you see it?
No, not really.
Well, let me give a different example. This is kind of critical. If I have two triangles like this, and I'm trying to prove congruency, it's clearly angle, side, angle, right?
Yeah.
It's not angle, angle, side. I would have to go the long route around to come up with angle, angle, side. Don't ever go the long route. Always go the shortest route. The shortest route is either going to be this, and this, or you can go in reverse, but the reverse is the same thing. In other words, if I go this, I still get angle, side, angle. Or if I go this, I get angle, side, angle. Go the shortest path you can go. In other words, I'm not going to say angle, angle, side. That's going the long path. Okay? It's more obvious here because it's very clear what the shortest path is. When I go up to the problem that we were just doing, it's not so clear when I have my triangle that looks like this, and the pieces of information I have are that side, that angle, and this angle. But I think you can see that it is the shortest way to go this way. Or, in other words, either go from here to here or go from here to here. But don't go the long way this way. That would be the wrong way. You understand now? It's a difficult thing to explain. In fact, at the beginning of the year, I was completely wrong. I was telling people clockwise or counterclockwise. But that's not the way to do it. You want to do the shortest path between the three pieces of information. You always end up with three pieces of information when you're proving congruency. Okay? So whatever those three pieces of information are, do it in the shortest path. This path here is shorter than this path here. You see why?
Yes.
Okay. I guess that's all I need to say on it. It's not always confusing. in this particular problem, I can see that it's a little confusing. It's not so clear that that's the shortest path. But in a lot of problems, there's no confusion at all. In other words, when I drew this example here, it's absolutely clear that the shortest path is to go this way, not to go around the horn. Okay, so back...
You did a good job.
What's that?
You said you did a good job. It made it simple.
Okay, good. Back to our two-column proof. So I'm trying to find one of these four reasons to make these triangles congruent. Well, I know that angle 1 is equal to angle 2. First of all, let me number these so I don't have to use letters. Let me call this 3 and 4. Okay, so first of all, angle 3 is congruent to angle 4 because they're vertical angles. And angle 1 is congruent to angle 2. Why? What's the reason?
I forgot that one.
They're alternate interior angles of parallel lines. It's the parallel line theorem. But if they specifically want it, it's alternate interior angles of a parallel line. If I draw two parallel lines and I put a transversal, 1 and 2 are alternate and they're interior and they're equal. Well, that's all we're looking at here. There's the two parallel lines, there's the transversal, 2 is equal to 1. And you probably can get away with just saying that, based on the fact that the parallel lines, that's what makes 1 equal to 2. Okay? Finally, the fourth statement is what?
Triangle ABE is equal to triangle CDE because side angle angle?
Correct. Perfect. And that's all you need to say. Side angle angle. Notice that side angle angle is exactly the same as angle angle side. So these three letters can be listed left to right or right to left without changing them. Okay, so there was our two-column proof. Are there any problems the rest of these that you want to cover tonight?
34.
Okay. Rotate 180 degrees. Let's first of all put our point on here. 3 comma minus 4. The way you rotate these is you connect it to the origin and you rotate the line. In other words, I rotate the line 180 degrees. So the point comes out up there. What are the coordinates on that point, do you think?
That'd be negative 34.
Right. So the rule is that if you're rotating a point 180 degrees, you just switch the signs on both the x and the y coordinate. That's all you do is switch the signs.
Now what if you're rotating 90?
Well, then it's a different rule. If I'm rotating 90, I'm not rotating to this spot. First of all, if you say 90, you have to say which way. If you say 180, it doesn't matter if you do it clockwise or counterclockwise, you end up in the same spot. But if you do it 90, and I say counterclockwise, then I'm going to move that line 90 degrees counterclockwise. And the point ends up there. What do you suppose coordinates are on that point?
3, 4.
I think it's 4, 3. Now, this is important. Because my 2 points, the numbers are close together, I can't tell from my drawing whether I've got it right or not. Okay? So let's use numbers where I will be able to tell. Just for the sake of figuring it out. Okay? Let's use 1, minus 4. Those numbers are far enough apart. I mean the 1 and the 4. Now, if I rotate that thing 90 degrees, I know exactly what the coordinates on that point are. What are they?
4, 1.
Right. In other words, you know you never change the numbers. You just either switch the numbers or change the signs on all of these. And if you use 2 points that are relatively far apart, you can visually figure out what to do. In other words, I didn't remember the rule. When you do a 90-degree counterclockwise rotation, what do? Well, the answer now is really clear. You switch the numbers, you switch the coordinates, and you change the sign on the y-coordinate.
Would it be the same for going clockwise? Just
Well, no, let's go counterclockwise. Let's go this way. Using the same 2 numbers where I will be able to figure it out. What are the points on that?
But that's clockwise, right, David?
Yes, sorry.
Yeah,
You're right.
So would that be -4, -1?
Yeah. I mean, I can look at it and figure that out. As long as I know that these numbers have to be either 4, 1 or +4, -1. I mean, either positive or negative, but I'm not going to have a 5 in there or a 3. And so if I pick a point whose numbers are relatively far apart, not 4 and 3, but 1 and 4, then I will be able to tell after I do my rotation what the proper coordinates are. And so I'll be able to figure out the rule. In other words, when I do a 90-degree clockwise rotation, I switch the coordinates and I change the sign on y. That's what I did up here, huh? I switched the coordinates and I changed the sign on y. So the rule is actually the same. I switched the coordinates. No, when I did this one, I switched the coordinates and changed the sign on x. On this one, I switched the coordinates and I changed the sign on y. So there is a difference. And likewise, using these 2 numbers, if I do a 180-degree rotation, I know it'll end up there. Well, that's got to be -1 plus 4, right?
Yeah.
So I don't have to memorize the rules. All I have to do is create a model like this, and it'll tell me the rules. But if I create a model like this, where my number is 3, let's say 4, 3, now when I rotate that, I can't really tell what my coordinates are down there because the numbers are too close together. You know what I'm saying?
Yeah.
As long as there's some slope there, then I'll be able to tell what happens when I do rotations. So that's what I pretty much tell everybody. I mean, you got a choice. You can sit here and memorize the rules for each kind of rotation. You know, what are the algebraic manipulations? But that's a lot to memorize. I don't know that. But I do know that I can always figure it out as long as I use numbers like 4 and 1, or 1 and 5, or 1 and 8. Just don't use 2 and 3, or 3 and 4, or 4 and 5. Don't use numbers that are close together.
So you want to use like 1 and 4 is great.
1 and 4 is terrific because it's absolutely clear as to what the coordinates on every point is, no matter the rotation, as long as it's a multiple of 90 degrees.
Sure.
Okay? Rotations are the only hard ones. Reflections are easy, right? In other words, reflections, I don't need numbers that are far apart. I can do the 3 comma negative 4. There's my 3 comma negative 4. If I reflect that over the x-axis, what are my coordinates?
3, 4.
And if I reflect it over the y-axis, what are my coordinates?
-3, -4?
Yeah, it's easy to do reflections. Translations are easy. If I'm translating this by this amount, I'm going to change the x by -2, and I'm going to change the y by +5. So I'm going to end up with 1, comma 1 if I translate it along that vector. And that's what you have there is 1, comma 1. In other words, translations are real easy. You just take that, add it to the x-coordinate, take that, add it to the y-coordinate. You good on 34?
Yes.
Okay.
So if we could go ahead and go to 36, is another one I have a problem with.
Okay. Where is that? Is that on a different page?
That's on the last page.
Okay. Construct the angle bisector. Okay. We talked about doing this. In other words, the fact that it's a triangle doesn't matter. I'm not even going to draw it as a triangle. I'm going to draw it like that. That's L, that's J, that's K, and I'm going to bisect angle L, right?
All right, I see. That's just like bisecting an angle.
Okay, so I'm going to put the needle there. I'm going to make an arc there, same arc there, so that those two distances are the same. Okay?
Okay.
Now what am I going to do?
You're going to measure out the angle.
No? I'm not using a compass. I'm not using a protractor to do this. I'm using a compass, right? Constructions are all compass problems.
Well, what I mean by measure out the angle is, I mean, you put the metal tip on one point and then move the lead to the other point.
Okay, you put the metal tip on one point, you make an arc. I didn't draw that arc very good. Let me draw the arc a little better. Draw an arc right there, like that. That's from this point. In fact, I didn't draw it good again. There's my arc. Okay, you with me?
Yep.
Now, without changing, in other words, you shouldn't change the compass setting this whole way. Put the metal tip there, make an arc the other way, and now connect that intersection point with the vertex, and you've bisected that angle. Using the same setting the whole way. Never change your compass setting on this. Because what you're really doing is creating a rhombus. In other words, this side is equal to that side, and that side is equal to that side. So I've created a rhombus, and in a rhombus, the diagonal bisects this angle. So that's why this method bisects that angle, is because basically you're creating a rhombus.
I think you mean
37?
37 I'm good with.
You know, David, we think that's it.
Okay.
Patrick feels that the ones that we've gone over, the ones that we need to go over, and we tried to take notes and get it done. You did a great job for moving through this stuff so fast, David. It's just, I mean, night before, it's amazing how, you know, cognizant that you put the whole situation for him. Really helped him out a lot, but I think we're done.
Okay, good. I'm glad that it was helpful. Good luck on your quiz tomorrow.
And thanks for giving us the extension, David, because I screwed it up. But
no problem.
All right.
All right,
I'll talk to you later.
Talk to you next time, probably next year. Have a Merry Christmas and Happy Holiday. Happy New Year.
You too.
All right, thanks.
Thanks, David.